So you have these notes that I gave you today, and again, it's notes, homework, and then the quiz review, which is tomorrow's assignment, and tomorrow and Thursday is also in that packet. So you already have the quiz review that you need for the next couple days. Okay, so don't worry about that. Now, though, we're going to do these notes and homework, and this is our last new material of Unit 2. So 2:15 for 1 day, quiz review 2 days, quiz on Friday, homework check tomorrow, okay? So what we're doing today is something called semi-log plots. We spend 1 day on it. There's one question, I think, on your quiz that relates to it, and there's one question that's on the AP exam that relates to it. So it's something I'm going to teach you. It's brand new. I could bet a lot of money that you've never seen it before, but we're not going to make a big deal out of it because you don't. Even if you forget it right now, when we review for the AP exam, I'll remind you, and you'll be like, "Oh yeah, okay, I'll get that one right." Okay, so. The reason I'm pretty sure that none of you have seen a semi-log plot before is because I'd never seen one, and I went to until last year, and then I went to the calculus teacher. I'm like, have you ever taught these? She's like, I don't even know what it is. So I don't know why College Board thinks it's important, but it's not difficult, so no big deal. Useful, I guess you would say. So let me read to you. In a semi-log plot, one of the axes is logarithmically scaled. We'll come back to that. In this class, it'll only be the y-axis, okay? With a semi-log plot where the y-axis is logarithmically scaled, exponential functions will appear linear. Now, I'm going to explain all that, but I want you to know that this is really the heart of what we're learning today. And here's where I'm going to explain it, okay? We have two graphs here, and it represents the English-American population in the United States from blah, blah, blah. Okay, so represents some real-life data. Right? The graph on the left shows the population using a normal scale on the vertical axis, and the one on the right is where the vertical axis is then logarithmically scaled. So let's take a look at the difference here. So this is a traditional graph. You can see the x-axis, and by the way, both x-axes are exactly the same. It's the y-axes or axes that are different. So this is counting like 1 million, 2 million, and so on. And then if you look over here, instead of counting by millions, these are all base 10s. Think about log base 10. That's what logarithmically scaled means. This is 10 to the first, 10 to the second, 10 to the third, and so on. So the y-axis is always going to be in a base 10. That's what it's going to be. Why? And so here's the first thing you need to know. The data, the points over here, are the same as the points over here. The data doesn't change. It's how you graph it. It's actually still graphed the same way. It's just it's scaled differently. So why are we doing this? All right. So if you look at this traditional J-looking graph, this is an exponential function right here. Okay. This is an exponential function because it's that shape, that J shape. It's in this form. And if you take a closer look at those points, the first, how many points? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You could make an argument that even more, they're all really close together. Like, how do you even tell the difference between this point and this point on this graph? They're so close together. But when we change the y-axis and replot the points, they all have their own, like, space, and you can tell the difference in these smaller numbers. And I want you to also notice that the majority of this graph is linear. See how it makes a line? That's what I was saying up here. Exponential functions on a regular traditional graph will appear linear on this type of graph. So this is linear, which is y equals mx plus b. That will always happen. Okay? So what about this semi-log plot justifies that this was an exponential model? Because it appears to be linear. The log graph appears to be linear. So all a semi-log plot is a different way of drawing your y-axis so that the data is more clearly viewed. Again, because in an exponential function, the data at the very bottom, or if it were flipped, it would be to the right, be really close together. those points really bunch up by your asymptote, okay? And then they get nice and big and spread out. But this is why we do it, okay? That's it. So let's look at another one. Here's another logarithmically scaled graph. You can see your x-axis is normal, minutes of something, and then look at your y-axis. These are base 10s, right? They're just written out. Like this is 10 to the 0. 10 to the 0 is 1. This is 10 to the first, 10 to the second, 10 to the third. So you can see it written as 10 to a power. You might see it written out as numbers, okay? Bottom line is base 10, 10 to the something power. And also you might notice how it's skewed differently. The graph looks a little different. I almost feel like it looks like it's been like bent or something. I don't know what the proper terminology would be. You don't ever have to draw one like this. You just have to recognize it, okay? So let me read this one. After Mrs. Morse tells one of her hilarious math jokes, it begins to spread around the school. You know how that happens. You guys start talking about it in all your classes. Like, isn't that so funny? Like, okay. The number of people, P, that have heard the joke after T minutes is graphed on the semi-log plot above, where the vertical axis has been logarithmically scaled. Which of the following functions could be a model for P? Well, what you guys should notice, again, we already talked about it. This is logarithmically scaled. And you could easily say that this looks linear. It doesn't have to be perfect, okay? But it's pretty close to a straight line. Since this is linear, the actual data would be an exponential model. It would represent an exponential. So all you're doing here is finding which one of these is exponential. And there's only one here that is. Remember, an exponential function is a times b to the x. That's not exponential, that's not exponential, that's not exponential, that is. So this is a really easy one. Usually there's like 2 that aren't exponential and 2 that are. So for example, you might see something that looks like this as an option, okay? If you saw this as an option alongside with this, how would you decide? Because they're both exponential. Well, something we need to remember about exponential function is your b value is your growth or decay rate. If the b value is greater than 1, your graph should be rising as you go left to right. That's why this is the answer. If this was the answer, all our points would be falling left to right, like a slope with a negative line, a line with a negative slope. Okay, so we'll see one of those again in a sec. Right? Next one, let me read to you. When we logarithmically scale the vertical axis for a semi-log plot, we are not changing the actual y values. It's still the same points, okay? Still the same points. To logarithmically scale the vertical axis means the equally spaced values on the y-axis are proportional, and the equally spaced values on the x-axis are linear, okay? And so we're going to look at another graph here in a second. But first, we have a table that gives selected values for the function f. Which of the following graphs could represent this data in a semi-log plot where the vertical axis is logarithmically scaled? So we need to match this data up with one of these graphs. First thing we're going to do, because this is going to help us with our last example here in a minute, is practice something that is important in this class. And we've talked about it several times. And that is when you are given a table of values, one of the skills that we have to be good at in this class that we'll see on the AP exam and we've seen throughout the year is given a table of values, you have to be able to say what type of equation that is. Is it a line? Is it a quadratic? Is it a cubic? Is it a exponential function? Is it a log? And the first thing we do is kind of look at what's going on in the table of values. For example, as I go from left to right with my x's, I am increasing at a constant rate, right? I'm adding 1, okay? As I look at the y's, the easiest one to check for is linear. Am I adding the same number as I go left to right? And clearly not. From 40 to 60, that's plus 20. Oh my gosh. Is plus 20. From 69, that's adding 30, and then it changes. So it's not linear. Let's see if we're multiplying by the same number. Am I multiplying the same number to this to get this, and then that same number to this to get this? I don't know. So to test that, remember you go in reverse. And I'll tell you, this is an exponential function. So what that number is your b. B is whatever you're multiplying as you go left to right, or dividing by as you go right to left. So like 60 over 40. Does that equal 90 over 6? 60 over 40, sorry. Does that equal 90 over 60? Yeah, we get 1.5, 1.5. So because we are multiplying by 1.5 as we go through this chart, that means that this is exponential. Okay? So the x are increasing at a constant rate, in this case adding 1, and our y values are proportional. In other words, we're multiplying by 1.5. That tells us that this data, if we graphed it, will be an exponential function. If you had a graphing calculator, you could put them in stat, graph it, just look at it, okay? But remember, there are times you have to say it in words. So if this data is exponential, when we put it on a logarithmically scaled graph, it will appear what? What will it look like? A line, okay? That was, remember, the really heart of what we're learning. So when we have multiple choice, it's good to eliminate. I think, I do know the answer. I'm acting right now. I think I can eliminate these two because they look a little curvy, right? They don't look like lines. And these two look like lines. But there's something else in these two that helps me get rid of them very quickly, and that is the y-axis. Neither of these y-axes are base 10. It's not 10 to the 0, 10 to the 1, 10 to the second, or 1, 10, 100. Neither one of those are that. That right away gets rid of those two. I've narrowed it down to these two, right? And if you look, the x-axis is the same on both. Let's look at the y-axis. In D, this is clearly a log scale, right? This is 10 to the 0, 10 to the 1, 10 to the second, 10 to the third. And by the way, B is as well. But all B is, look closely at it. This is going from 10 to the 0 to 10 to the 1. It's just this part of a graph blown up, right? It's only from here to here. It's just drawn a little bit bigger. So that's what you're seeing here. So these are both logarithmically scaled. But what are the points? We can now narrow it down to which one by looking at the points. We should have a point that is 140 and a point that is 260 and so on. Well, in B, we don't ever go higher than this number. This number is 2, 3, 4, 5, 6, 7, 8, 9, 10. So we don't ever even go above 2 in this graph. We go up from 140 and 260. So D would be your answer. Most of your homework is this type of problem, okay, where you have to match up information with a table of values. We also have another type of problem. So there's basically 3 types. Here's the second type, where you are going to plot points. So we have a blank logarithmically scaled graph. Logarithmically. 5-syllable word. I have to keep saying it and I keep messing it up. And we're just going to plot these points on here and label them, okay? So keep in mind how this is labeled. So if I want to do 0 to 100, okay, so here's my 0, here's 100, and so between 100 and 1,000, we're counting by 100, okay? So this is actually 200 right there, 100, 200, 300, all the way up to 1,000, okay? 125, so that's going to be between 10 and 100. So once I get to 10, I'm counting by tens, right? This is 10, 20, 30, 40, and so on. So 125 will be in the middle of 20 and 30. Stop me if you're missing something here. 2, 7. So 2 and then 7 is less than 10. So we're just going up to, there's 10, so it's sometimes easier to go backward. 10, 9, 8, 7. Somewhere around there. 3.2 and 800. Okay, so 3.2 is between these two. Let's look at how our x-axis is broken up. This would be 3.2, 0.4, 0.6, 0.8, and then 4. So 3.2 is right here. Up to 800, that would be between 100 and 1,000. So again, it's easier to go up to 1,000 and go back to, right, to get to 800. So about right there. And the last one, 4.6, 1.5. So 4.6, this is 246. So here's 4.6 where my pen is. And then this line is 1, so right in the middle would be 1.5. Okay? So there's no 0 on the y-axis. It starts at 1 because of an asymptote. But being able to plot those points. Good with that? Okay, the last question, if you're like, I get this, I'm good, you still need to listen to this one. This one is important, and the very last thing I'm going to tell you about this one is going to help you on the quiz review and quiz, which I'll go over again tomorrow, but it'll help you be less confused tomorrow. So just stay with me for a second. All right, so here we have, so let me just read to you. As we've seen, if we graph an exponential function on a semi-log plot, the graph will appear linear. We've got that. In these cases, we can create a linear model for the graph on the semi-log plot, right? So let me explain. Given an exponential model, a times v dx, the corresponding linear model for the semi-log plot is given like this. Because your exponential function looks like a line on the logarithmically scaled coordinate plane, your slope-intercept form has a little extra job that we have to do it. And I'll explain that more in a second. But first of all, look at this. They're calling this the linear model. What the heck is all this weird log base n blah, blah, blah? Don't worry about it. That is your slope. That is your y-intercept. All that is saying is this, okay? But our m and b are in log base 10 form, and I'll come back to that in a minute, okay? So let's take a look at what we have in example 5. Right? The semi-log plot above corresponds to the data for example 3. So I'm going to go back and find my example 3 and put it up here for us, just so we can have them together. So it's the same table of values we already did some work with. Okay? So example 3, we just dealt with a second ago. So I'm just going to put it here so we can look at it. Right? What we're asked to do is write a linear model and an exponential model that represents this information. Okay? So the linear model here, we need m and b, right? To write something in slope-intercept form, we need a slope and a y-intercept, m and a b. When we get to the exponential model, we need an a and a b. And be careful, they're not the same b, right? In a slope-intercept form, b is your y-intercept, where your line hits the y-axis. And the b in an exponential model is what you're multiplying by as you go left to right, okay? So what I'm going to do is recreate this table, but I'm going to change it a little bit, and I want you to change it the way I change it. So I'm going to take this table, and I'm going to say x and y. I'm going to add 0 in, because they didn't give me what the 0 is. I'll come back to y in a second. I also, I'm going to just steal the 1 and the 2. That's good enough. 3 points will be enough. There's more, but this is enough. So I already know this is 40 and this is 60. I want to know what this is right here, because that will tell me my b value. Close to it anyway. I'll come back to that. So let's just fill in this number right here. So remember, as we went right to left in this chart, we multiplied by 150. That's how we went from 40 to 60 and so on. If you want to go backwards, you would divide by 40. So to find this number right here, don't write under it. You need space, actually. You need to do 40 divided by what? 40 divided by what? Yes, 40 divided by 1.5 is going to give me that number. So when I do 40 divided by 1.5, I get 26 point blah, blah, blah. Always see if you can write it as a fraction so you don't have to round. So math, enter, enter. Yep, I'm going to write that as 80 over 30. I'm sorry, 80 over 3. I'll put that in. 80 over 3, right? So now I know the y-intercept, but remember, these points that make a line, right, it should, because we already know it's an exponential function, makes a line, is on a different scale. So what we have to do is make one more level of our XY chart. Every period that I write this, I say I'm going to make my chart bigger so I don't just squeeze and I won't remember to do it. What we're going to do is log of our Y values. So really, what we would have is log of 80 over 3. Sorry, I'm squeezing. Log of 40. Log of 60. And those are going to be numbers we get right out of our calculator in a minute. That will be our M and our, well, we'll find our M and our B using those. So let's just start with B, because we know what that is. It's where X is 0, right? That's the point on the Y-axis. But instead of using 80 over 3, because it's the linear part of it, that M and B are in log base 10 form. So simple. All you have to do is log, you can use your log button because that's base 10, of 80 over 3. 80 over 3. And that would be, my y-intercept would be 1.426. Okay. What is my slope? Slope, AROC, all the same stuff. Guys, you can take any 2 points off of here and plug it into your AROC formula. Slope, AROC, call it whatever you want. We reviewed it yesterday, if you remember. Change in y over change in x. Pick any 2 points. I dumbly used this point first period and had to deal with a fraction. Let's ignore that one. Let's use these 2. But remember, since we're working with the linear one, we're going to use the log row. So log of 60 minus log of 40, those are my y values, over x's, which is 2 minus 1 for those 2. Right? And this is just calculator work. Your denominator, 2 minus 1 is just 1, so we're not going to do anything with the denominator. We can just simply type in our calculators log 60, close your parentheses, minus log 40. Go ahead and do that real quick for me, guys. Let's find that numerator. Hi.
Hey.
How are you?
You saw the email?
Yeah.
That's awesome. Yeah. That's really an honor. I mean, GD Biggie doesn't mince words.
Yeah.
He's very straight up. So
Yeah.
that's awesome.
Well, there's
really good.
Mary Sullivan, the staff
Yes.
developer.
Yes.
She uses my Canvas videos and everything to help train people in South County, so she
That's awesome,
has kind of
of course.
said she likes the way I do
No,
my
you're
class.
bold, and I didn't know she communicated directly with you. Like I didn't know you were at that time, you know. So I would like, I'm not that guy. Cause my school, you can't come in, no visitors.
Mm-hmm.
But I wanted to make sure I at least you were cool with
Of
it.
course, yeah.
Yeah. So I didn't mean to speak out of turn, but
Oh, no.
that's really exciting and cool.
Yeah,
That'll be a highlight. We'll make a big deal of that.
Oh,
That
thank
is a
you.
big deal.
Thank you. I appreciate it. These are my really good class.
Yeah, it's long wrestling that. You've got to
Oh, wrestler. Look, Lily's
All the
in here.
wrestlers,
Evan, I
yeah.
have Josh.
It was awesome. It was such a cool team, and I was really
Oh,
proud of
good.
great group of seniors and underclassmen. Wrestling, and the energy in the wrestling gym, folks.
I have got to get to one.
You do.
I do.
Unfortunately, we're done with them.
Okay, next year. All right. Yeah, so anyway, the lady in charge of AP Pre-Calculus in the country wants to come observe my class. I know. I was like, wow, pretty cool. And she like they're having a whole team visit to just see my culture in the classroom because apparently they like it. Not this period. They are coming to my 7th period. Anyway, it was a nice compliment. Okay, what did we get, guys? Did you get an answer here? You should get a decimal. You got yucky decimals here. You should have gotten 0.176. Yeah? So log 60, close your parentheses, minus log 40. If you didn't, I'll come back and help you in a minute. Let's just finish this up because we're actually almost done. So I just plugged in my slope and my y-intercept, okay? So what you have to remember is with the linear model, you have to use that row, okay? You have to do the, not y, the traditional x and y, because it's not on a traditional x and y. You have to use the log y, okay? For the exponential model, what we're talking about is these points right here, okay? That's these points. So we already know b is 1.5. What are we multiplying by as we go left to right? And if you remember, A is your y-intercept. Where does our graph touch the y-axis? Well, we didn't know when we had this information, right? We would have had to go backwards, which we did here. So that would be 80 over 30. So that's it. Y equals 80 over 3. That's my A. Here's my B to the power of X. Right? So that has a little bit you have to do in it. That has a little bit of work in it, number 8 and then number 9 on your worksheet. Okay. So, remember I told you there was one more thing I'd tell you at the end, the very end. When you get to the quiz review, and I'm saying this in case you're absent or you start working ahead, the one question that's on your quiz and your quiz review, unfortunately, is slightly different than this. It gives you just understand, I'll go over it tomorrow, but the question that you have to do on the quiz and the quiz review does not have this logarithmically scaled. It actually is graphing this line on a regular graph. It's a little weird, not hard, I just have to tell you something, but I'm just giving you a heads up so if you're not here, but I'll talk about it tomorrow, right? So the worksheet C7 is attached to your papers there. I copied 1 through 10 for you, but you only have to do 1 through 9. You do not need to do number 9, okay? The key is already on Canvas. There's a lot of pages, there's a lot of multiple choice. So what I did, guys, is here's number 1, here's number 2, here's the answers to 3 through 7, multiple choice, since I can't fit all the pages up. And then the last 2. But it's on Canvas if you want to see every page or see it bigger. Because when you get, it's multiple choice, B or C, I feel it could be the answer for that one. I think it'll make sense when you get there. Okay. I think it's printed at the top of your worksheet, isn't it? C7? It should be right after the page we were just doing. Does it not say C7 on it? I guess I didn't put that on there, right? I don't know.
So we're not doing 1, 2, 3?
Oh, I think it just, does yours just say worksheet A? Okay, it's C7. Sorry. I should have put that on there.
We're not doing 1, 2, 3 though? Just 5, 6, 5?
You're doing all.
I don't know. Oh, I know.
This is number 1. This is number 2. 3 through 7. Of course not. I was mad at him for saying that. I do what? Oh, you're wrong. Oh, it is?
Yeah.
I wonder if is it here?
Yeah.
Oh, maybe during my planning.